Scientists are studying how trees emit gases that form aerosol particles and cloud seeds, as this process plays a significant role in cloud formation and our climate. Understanding these processes is crucial for predicting future climate changes and incorporating them into climate models. Researchers are using a cloud chamber to study specific vapors and simulate different atmospheric conditions. Exhaling. Biomass. Baseline. Simulates. Cubed. Cylindrical. Aluminum. Foil. Oxidation. Photosynthesis. Crucial.
You're listening to Shortwave from NPR.
Sometimes when I'm driving through the mountains here in the Pacific Northwest, I see small clouds rising above the trees, like little puffs of breath. And it's not just a metaphor. Those trees are exhaling, and it's forming clouds.
Plants emit gases that form aerosol particles and cloud seeds.
Dr. Lubna Dada studies these particles as part of an international experiment named CLOUD, all caps. She and fellow atmospheric scientists are interested in, you guessed it, cloud formation.
There are several processes that lead to cloud formation, and the most important thing to keep in mind is that each cloud needs a cloud seed so that they can form something on top of it. And this seed is usually an aerosol particle or a particle that is suspended in the atmosphere, and it comes from different sources such as sea spray or dust or combustion processes or biomass burning.
So some aerosols are natural, while others come from human pollution.
Just think about the process of water condensing on your window when you cook. So these aerosols are acting just like your window. So they form and then they act like a surface which can take in more gases to grow to form this cloud.
In addition to producing rain and snow, clouds play a huge role in our climate. Some types of clouds act as a layer of protection between incoming solar radiation and the Earth, and they cool the atmosphere. Other types of clouds act like a blanket, and they trap heat. So knowing what type of clouds form where and how long they stick around is important for scientists who want to predict how our climate will continue to change in the coming decades. But many current climate models don't account for these warming and cooling effects of clouds at all, and in particular, the role that aerosols play.
This is the biggest uncertainty in climate science at the moment.
So today on the show, we've got our head in the clouds, and we're looking towards the trees to tell us more about the mystery of cloud formation and how to better model the changing climate. I'm Aaron Scott. You're listening to Shortwave from NPR. In order to incorporate clouds into our models of how the climate is changing now and to predict how it will change in the future, Lubna says we first need to look to the past to understand how clouds behaved before the Industrial Revolution.
We don't know how much humans contributed to the change of the background cloud condition. So we need to know what the background was so that we know how much we contributed in order to understand the future, so that we can form this baseline where we can add this contribution of anthropogenic emissions or human-like emissions.
Lubna and the team of cloud researchers are trying to fill in some of these gaps, past and present, using a steel chamber that simulates our atmosphere.
The cloud chamber is basically the atmosphere in a box. It's around 27 meter cubed, so it's the size of a room. It's a metallic cylindrical chamber that is covered with tape that looks like aluminum foil on the outside, and it's made of stainless steel so that we can wash it when we need, if we have any of the sticky things sticking on the wall on the inside. And it also has fans for homogenizing the air inside. It has specific lights that simulate different levels of the atmosphere. And it's the most important thing about it, and which makes it the number one and only chamber in the world that can do such experiments, is that it's super, super clean. So there are no contaminations. What's inside is what we put inside.
Lubna and her team can study specific vapors by injecting them into the chamber. They can also mimic other atmospheric conditions, things like light, temperature, and humidity, depending on the geographic location they want to simulate. And then, can you grow clouds in it? Like it literally kind of grows little baby clouds?
Yes. So in the whole steps from going from the gas phase to the oxidation of these gases, to them forming the very, very tiny particles. It grows further and further and further until it reaches something that is acting as cloud seeds. And then we are also capable of changing the pressure and the water inside the chamber, so we can form clouds in the cloud chamber.
That is so cool.
So wherever you can imagine around the world, we have tried at least once to do.
So, Lubna, the recent study that you led with the cloud experiment involved organic chemical compounds that plants produce. Can you tell us a little bit about these natural emissions and why they're important for plants? What do they do?
So they are organic molecules that are formed from photosynthesis. So the plants are eating, I would say, and then they are producing organic molecules, and some of these molecules are also released so that the plants can communicate between each other.
There are different types of these emissions that play a crucial role in cloud formation. Two common kinds, called monoterpenes and isoprene, have been studied in the past. But there's another kind, called sesquiterpenes, that Lubna says have been largely ignored until now.
We were not able to quantify them this well before because they are so little emitted in the atmosphere to start with, and then they react very quickly, so we're not able to capture them when they are still in the gas phase, or the original shape they were emitted from the plant. And we did not think that they would contribute as much as we found in this study, that they actually contribute more than both of the other types of terpenes at the same concentrations. And then there were also recent studies that showed that these sesquiterpenes are like communicating agents when the plant is stressed. So there were studies where they actually put a tree in a chamber and they started subjecting this tree to some sort of stress, and found that drought, for example, was one of the causes that caused sesquiterpenes to be emitted much more than even monoterpenes from the tree. So that's why we focused on sesquiterpenes, so that we can see whether in a future that is subject to more and more stress on the plants, would that do a change in the total emissions from plants and their aerosol and cloud seed formation capabilities at the end.
And so if I'm understanding this, when trees are stressed out, they release these sesquiterpenes, or release them in greater amounts, and those form particles in the atmosphere, which lead to the formation of clouds, which reflect the sun's heat. So basically, like, stressed out trees are playing a role to cool our atmosphere?
I would even say stressed trees are trying to cool themselves. So it's like the trees are affecting the climate while the climate is affecting the trees.
What do your results mean for current climate models? And what do we need to do to kind of tweak or change them?
Knowing now that these sesquiterpenes are actually contributing a lot to the aerosol particles or the aerosol population, and thus the cloud seeds, we suggest that they are implemented in the current climate models. So this is one step further than what we knew before, that trees contribute to aerosols and to clouds. And now we have a better estimate of what was happening in the pre-industrial era, what is happening now, because we have emission inventories that tell us that we have this amount of these terpenes available in the atmosphere. And now our studies have shown how many aerosol particles are formed from these gases, or from sesquiterpene in specific, when it's present in any of the locations. So we improved the models by also saying how many aerosols are formed from this sesquiterpene.
I love this idea that trees are doing a little geoengineering of their own to fight back against climate change. But it also seems like this effect could have diminishing returns as trees die due to drought and rising temperatures and the wildfire that follows. So in thinking about how to add this to climate models, do you also have to think about how this cloud formation effect might weaken in the coming years?
Yeah. So what we actually look at is the migration of these kind of plants. So if we want to think about drought, for example, or even like any kind of stress, and think about plants as us. So if you and I feel that we cannot live anymore in this specific location because it's too hot, we would start migrating north until we reach a location where it is no longer hot for us to be there. And I think this is what also has been shown by scientists, that actually the biomes or the vegetation is migrating north.
Or higher elevations, climbing up mountains and things.
Yes, that's true. And then it is kind of like not possible anymore to see the same things we are seeing now. And that's what climate models are also doing. They are taking into account this migration of vegetation to take into account the type of emissions from plants or trees that we are expecting in the future and so on, so that we can model what happens in the future in terms of emissions and then aerosols and in turn clouds.
I love this. It's going to make me, as I drive through the mountains and the forests and look at the little puffs of breath of these trees forming clouds in the sky in an entirely different way. Thank you so much, Lubna, for bringing us this research.
Thank you for having me and introducing my work to many people who are listening.
Before we go, I want to thank our Shortwave Plus listeners for always having your head in the clouds with us. Your support is the wind beneath our aerosols. And if you're a regular listener but you haven't yet subscribed, we'd love for you to join so you too can enjoy the show without sponsor interruptions. Find out more at plus.npr.org/shortwave. This episode was produced by Rachel Carlson and edited by our managing producer, Rebecca Ramirez. It was fact-checked by Britt Hansen. Our audio engineer was Maggie Luthar. Beth Donovan is our senior director, and Anya Grundeman is the senior vice president of programming. I'm Aaron Scott. Thanks, as always, for listening to Shortwave from NPR.